Hi there. We're going to be showing a basic connectivity testing and a little bit of explanation about our network and why we chose the shape that we did. Our network is a standard hierarchical topology with a distribution and access layer, both running over layer 2. Of course, spanning tree is the protocol that we're using for this, per VLAN spanning tree, or rapid per VLAN spanning tree to be more specific. And we're going to start off here with a quick connectivity test. We're going to be doing some pings, which are coming from a client hooked up to our switch 5 here, switch 2. Now, it's pinging the switch virtual interfaces on all of our other devices. And we can see that we do have a connection to all of them. We're going to be showing a quick test too of our SSH connection, which will actually be coming from something hooked up to switch 5 here. Now, our SSH can reach out to pretty much all of our devices as well. Regardless of what the topology is, it should be able to find the IP address of each of these. So we went with a more traditional layout for our VLANs in this network. Of course, we wanted to make sure that we had a couple testing VLANs just to show off the functionality of them. With our VLAN 4, which contains all of our IP addresses, is our management VLAN. This will allow our IT department to SSH in and connect to various devices around the network. Using this, we can reach all the SVIs and have all of our devices IP addressed and working on this network. We have VLAN 6 as an employee network, mostly just for testing in this environment, but in a real deployment, this would be our main network for our employees to actually be on. Now, as you can see, there is no VLAN 1 on this network. We didn't want our native VLAN to be VLAN 1. We didn't want untag frames to go on there, and we didn't want attackers to try and tag their frames with VLAN 1 and have free access to our SDP environment. Instead, we have chosen VLAN 81 for our native. This is not only just a little bit harder to guess, but it provides a little bit more security as well. It allows us to have a bit more customization of our network. Next up, we can see that we have VLAN 80. This is a black hole VLAN. What the purpose of this is it allows us to have all of our untagged traffic go into this VLAN. All the ports on our switches are shut down. No one else can plug into these and actually get anything out of them because they are shut. And we also have port security on these. But if someone was able to no-shut a port on here and get their computer onto this network, they wouldn't actually be able to go anywhere because naturally they would be put into VLAN 80. Now, VLAN 80 actually can't go across any of our links. Our trunks won't allow it, meaning that they are now stuck onto this switch. So this gives us another security advantage. It means that if anyone is able to get around our port security, they're not going to be able to get over our trunk security. Only VLANs that we have created, particularly VLAN 4, VLAN 6, and VLAN 81, are able to go over our trunk links. Of course, this is mainly for security and allows us to see which traffic is coming from where. So here, I'm going to show a little bit about our spanning tree topology and the choices that we've made with it. To start off, we're going to start with our root switch, which is this orange guy right here. And we can tell that it's the root because all of the ports facing it directly connected are our root ports. And we can see that all of its ports coming out are designated ports. This defines it as the root switch, and we chose this device specifically because it is not only on our distribution layer, but it's also the fastest device on our network. It and switch 1 here are both very modern Cisco switches, and they can handle a little bit more traffic than the older ones down here, like switch 2 and switch 5. Now, switch 3, our center one here, is connected to all of our devices, so it's also an important portion of this spanning tree network. It has both of our ether channels coming in through it. Now, our ether channels are running on LACP, but because there's 2 of them, and there's a connection between switch 1 and switch 4, we had to come up with a solution to make sure that there wasn't a bridging loop here. Now, this yellow port actually designates that this is an alternate port. So if our ether channel here was to go down, it would immediately swap over to this ether channel. This is also effective because switch 1 here is also our secondary root switch. So this is going to act as our backup in the case that switch 4 actually fails, meaning that this ether channel serves a double purpose now, as it's going to be another high-speed connection towards our new root switch in the event of failure. Of course, this will neuter our network a little bit. We have some blocking ports down here attached to 10 megabyte links. Now, these 10 meg links are not the best to use, so we put these into our network just to kind of show how to optimize our traffic. these are more or less going to be a backup, and they're not going to be used until another link fails. So for switch 5's case here, it's never going to use its 10 meg link until our main link to the root switch fails, in which case it'll find a new path automatically coming this way. Now, we've set up a couple different SDP enhancements on our network here, including root guard, BPDU guard, and port fast. Root guard, of course, will keep a rogue device from taking over any of our root positions. So if we were to plug in a malicious switch or another device that was claiming to have higher priority, it wouldn't be able to take over our network. This is also protected by having port fast and BPDU guard on pretty much everything that we can. Now, BPDU guard is going to stop us from receiving BPDU packets from devices that we aren't looking for it from. This will place the port in an error disabled state. This not only stops rogue switches from being able to change the topology, but it also keeps our ports set to port fast from receiving any BPDU packets. This avoids bridging loops. This is also supported by having BPDU guard on non-trunking ports. So we're going to be showing off how we set up our trunk links. To start off with, we're not using DTP. We don't think dynamic trunking protocol supports what we're doing, and we think that our own judgment is better than what that protocol could do. We're also not using ISL for any of our encapsulation. We're using 802.1q trunk links, as we think that is currently the best solution and the most compatible. Now, we have a couple VLANs. Of course, our communication and native VLAN is 81. So as we take a look here using the show interface trunk command, we can take a peek at how our trunks are working. Our native VLAN is of course set to native VLAN 81. Now we can see that we have our two regular trunk links coming off of this switch. This is our root switch, by the way, and we can see that port channel. Next, we're going to be using the show spanning tree active command and taking a look at how our spanning tree is working from our root switch. As we can see, being a root switch, everything is set to forward. This is because there are no dead links attached to our root switch, as all ports on the other switches will be root ports facing us. Now, if we were to take a look at some of our other switches, we would see some of these in different states, such as blocking. So as we can see, we move over to switch 5 here, and we can see those forwarding states, as well as a blocking state. And we can see that under that role, one is set to root, one is set to alternate, and one is set to designated. So now I'm going to show the ether channel configuration that we're using. Using the show ether channel detail command, we're going to pull up some information here. This is coming from our root switch, which is running one ether channel heading to our center switch on switch 3. And from here, we can take a look and see that we are currently running LACP to communicate here. Now, we like LACP because of its load balancing characteristics. Currently, it's set to a 4-4, meaning 4 packets down one line of the ether channel, 4 down the other. And we can see that this current side of it is set to passive mode, while switch 3 is set to active mode, meaning it's the one negotiating the LACP communication. Alright, so as we can see here with our client on switch 2, it's currently using port 1 as its main one. They're blinking together, all of our pings are actually going through there. This is because this is the fastest way back to our destination. It's currently taking our port 1 up through switch 1, which then goes straight over to our root switch, which is what we're pinging. So if we were to unplug this, we would see that we immediately fail over to port 2. This is going through our slower link to switch 3, and then up to switch 4 that way. However, if we were to unplug both of these and then put our main link back in, we have to see how fast it does reconvergence. So that happens, and it takes a few seconds, and we'll wait until our VM here can actually continue pinging again. We'll plug this back in as it won't be of priority anyways. Alright, so here we are with PVST instead. As we can see, PVST is still declared the same port as our fastest. This is still our primary port heading back to switch 4. And we'll pop it out. The failover, again, works the same way as rapid per VLAN spanning tree. It has failed over successfully. However, when we take both out and try and get that convergence time to go, now is the real question. So it still takes a minute, but we're going to have to take a look back at our VM here and see how long that takes before it can continue pinging again. So it's clear that rapid per VLAN spanning tree takes about half the time to converge as per VLAN spanning tree, making this a pretty effective tool to put into your networks. So the problem that we're presenting is a CDP flooding attack. Now this can be done in a multitude of ways. We're using a Kali Linux distribution to do this against our switches. The reason why we wanted to pick this as the problem for our network is that a CDP flooding attack is very easy to do and very hard to counter. There aren't very many security features built into CDP, and doing this seems to be able to work on most networks. Throughout all of our research, we haven't found an effective means to fully stop this. So we came up with our own solution, and we're justifying it here. So here, I've got my Kali Linux distribution. I'm going to be using an interesting tool here called Yersinia, if I am pronouncing that correctly. What this program is great for is layer 2 attacks in general. Using the Yersinia-G command, we're able to open up a graphical user interface for it. Now taking a look here, we can do a number of different layer 2 attacks. CDP is the one that we're going to go on here. As we can see, Yersinia has already sniffed a CDP packet coming out of our switch 3. So by setting it to spam the CDP table, we're making it seem like there are a lot of neighbors, and I'm talking tens of thousands here. This is actually pinning the switch's CPU at 100%, making it react a lot slower, and in a production network, most likely dropping frames. So we're going to take a look at what this looks like over on the switch. So firing up our switch, we can see that it is still working. We're going to use the show CDP neighbors command to take a look, and we can see our normal neighbors at the top there. However, then there is a lot of very, very obvious garbage filling this switch up. And after a couple minutes, this will actually be able to take the switch down. And in production environments where there's a lot of load and traffic going through them, this can happen even quicker. Now this happens because CDP is an open Cisco protocol. So this is how Cisco devices are supposed to communicate with each other and recognize each other. As we can see, however, the platform here is Yersinia, and we can notice a couple discrepancies in the traffic that very obviously states that it's not real. So there aren't a whole lot of ways to protect against this. Most people just turn off the ability to receive CDP discovery and packets. In our case, we want to keep the CDP protocol around, as we would like to use the benefits that come with it. So we're going to try and enable some port security here.
So on switch 3, we have port security configured on port FA0/24. So for that, we enter the commands switch port security and then switch port security MAC address sticky for the end device that we always want on that port. Then switch port security maximum of 1, so only one device is allowed on that. And then switch port security violation restrict, which drops all packets from insecure hosts. So here we do show run interface FA0/24, and we can see all our configs for switch port security on that interface. And we can see the end device that we always want, its MAC address has been placed in there, and we can also do show port security, which shows which port is in port security mode, which is port/24, and switch show port security interface FA0/24, which shows that port security has been enabled and is in restrict mode and is secure up. So this prevents the rogue end devices to connect into that port 24 on this switch and prevents CDP attacks.
So one more time, we're going to fire up Yersinia, and we're going to do a CDP flood attack. We can still see the switch's name from a CDP packet, and we can't stop them from coming out. However, if we were to run another attack against it, we would notice that there is a big difference here. The CDP packets still flood out, however, they're not making it anywhere. If we were to look at our switch, we can see that there are error messages showing a violation and a locking of the port. It's now restricted. So if we take a look at our CDP neighbor table on that switch, we'll be able to see that there's only the switches that we intend to see. That massive pile of junk that we saw before, it's not showing up.